करना है कि नहीं करना है. ठीक है, अब one guy makes 825 and there is another company who also makes an 825. Almost the features the same. Okay, this guy is consuming, let's say, 100 watts, let's say, just for the figure, and this guy is consuming 110 watt. Okay, and this guy is operating at 2 something point gigahertz, and this is operating at 2.4 gigahertz. Which one you will buy? I believe most of the people will select this guy. Okay, why? Because this guy is having performance, it's faster, it's better, the frequency is higher, right? So everyone will think this will perform better. Power ठीक है, चलो हैंडल कर लेंगे, थोड़ा पावर ज्यादा है तो क्या हो गया, फ्रीक्वेंसी तो अच्छी है ना, अच्छा परफॉर्म करेगा, फास्ट चलेगा, आई कैन प्ले गेम्स, गेमिंग परफॉर्मेंस अच्छा होगा, वीडियो ग्राफिक्स अच्छे होंगे. Okay, so frequency compromising frequency can be serious. So you cannot compromise frequency. Okay, you can reduce capacitance, but with some certain ideas. Like what? Yes, you can change technology, but not every time. Not every time. Not every time you can change the technology. Okay, this can work only once, isn't it? Because let's say you are working in 90 nanometer, you plan that, okay, I want to have a product which has a less power.
Vinay
So
ji,
next year, yes, sir.
you want to have a break, coffee break?
Uh, that's okay. It's okay. The coffee's here, but
Okay.
I
So
will
just
just,
I'll talk to students.
no
Will you have a
problem. We
coffee?
just, okay.
Or you will
I
complete
think
this.
this is,
Your
yes, this is
timing?
the last
Okay.
slide. Yeah.
You complete. Okay.
Yeah. Yeah. So you can change the technology, but not every time you can do it. There's not every time you can change technology. Okay, so it's only one time card you can play. Then you can always do improvisation of the structure or the architecture. You can reduce the node capacitance by duplicating the logic, duplicating the fan out for. Because, for example, if there is one buffer who's driving a huge capacitance, right? So this guy will consume more power. But if you put another buffer to it, parallel to it, so now both of them are able to rise the capacitance much more faster as compared to this was the previous rise time. Now the new one would be a little faster. So there would be less power consumption by this design. Okay. Then you try to balance the differential paths to avoid glitches. You handle the fan out. You place proper buffer at the clock network. And these days, most of the people are dependent on these techniques. Clock control, clocking control, which you may commonly see in your mobile phone. Okay, so that means you don't operate certain part or segment of your circuits which are not used by the user. For example, if you are not using a Wi-Fi, then probably the mobile phone will turn off your Wi-Fi for a while, or he will just keep it connected, but he will be not transferring the data so that it consume power. For example, you just turn off the display when the user is not looking at it or not using it, or you. And the best part is to reduce the frequency reduction. Have you noticed that when you don't use mobile phone for half an hour or something, you find, and when you turn on the mobile phone for a few seconds, the mobile phone is responding slowly. I mean, he's not able to run at the fastest performance. Why? Because when you are not using the mobile phone for, let's say, half an hour, so mobile phone reduces frequency by like 20%. Then if you don't use for another half an hour, it reduces 20% further. Then another half an hour goes by, he reduces 20% further. So what is happening? He's reducing the frequency slowly and slowly if the user is not making use of the product, and so that the power comes down. The same happens with the laptops. When you are not using laptop for a while, they shut down the display, they go in the sleep mode. That is different, but at the same time they keep on reducing the clock so that the power can be controlled. And once the user interrupts that, okay, okay, I'm back and I'm using the product, so automatically the frequency is pushed higher. Okay, so these are the clocking control by method which the power consumption is being controlled. Okay, so this was power. Timing maybe I will discuss tomorrow. This is another aspect of the design. I don't want to push many things on the same day. Okay, so what we will do today for is that we will go for the hands on. I will give some introduction about Microwind, that how does it works, and what kind of stuffs you can make. Mhm. Okay, So everyone is I believe everyone must have installed Microwind, isn't it? So I just clear the screen and share it. Okay. I believe everyone must be having a look at the black screen, which is of Microwind and the basic template. Can I get couple of yes or no so that I'm just assured? Okay, thank you everyone. Okay, great. So let's move ahead with the design of something. So I will request everyone to stay away from their mouse and don't try to follow through that. Don't try to copy and repeat what I'm doing. Don't worry. I mean, there are videos available on internet which many people have done it, or even on the Mac channel you can find on the YouTube the same videos. So you can repeat from there. Okay. So today we will just, I will give you something which you can practice tonight or maybe tomorrow morning whenever you find time, making of an inverter and few things about the software. Okay. So when you start the software, by default, it opens with 45 nanometer, or I believe this one is.
Your voice is low. Your voice is low.
Voice is low. Okay. Let me have the microphone back in my hand. Okay. Hmm. Okay. So you can go to file menu, select foundry, and select Cmos 012. So this is, by this way I'm forcing the software to select 0.12 micrometer technology. So you can work on any of the technology root file. It will behave the same. Okay, not the same. I mean, obviously the performance would be different, but the using of the software will be the same. Okay, so uh, on the top side you see the some menus available, and also there is a toolbar with the help of which you can get some quick menu. I will not much talk about the how to use the buttons and what buttons does this, because I am sure that within 10 minutes you will be familiar with all the buttons. Just press everything, because nothing will explode from your laptop, nothing will damage your computers. So you just keep on pressing anything and try to understand what it is showing. Okay, it's so simple. Okay, so on top and side you will find that there isn't something which is a multicolor screen, which is called as palette. We call it palette. Okay, so with the help of which you can draw anything you like. So you see that the dots which are shown on the screen, this is a p-type substrate, and on the lambda grid. Okay, so on the lambda grid we can draw anything. So let's draw an n-type transistor. So I take an n diffusion layer and I just draw a block. So this is around, I just say that this is 6 lambda wide and 14 lambda long. Okay, so on the bottom left hand side over here, it shows the dimensions. Okay, at the same time it was showing you dimension, that how big or small you're drawing. So that is your n-type diffusion. Okay, on top of it I take a polysilicon layer. I just left click once on the polysilicon, and by keeping my left mouse button click, I just draw a block in between. So that's a very basic NMOS transistor. I just take this 2D cross section and draw a line in between. So it will show me the 2D cross section. So this is what you see. This is your drain and source, and the gate material, the red one.
Yeah, this is one of the very good feature of Microwind, where you
Yes.
can see the 3D, where we cannot go and see every time fabrication.
So this is how you can see the 2D cross view of the transistor, and also the three-dimensional view, that you can visualize that how actually the transistor has been fabbed out. So here you have the drain, and then left hand side you have the source, and top of it there's a gate material. Okay. Okay. So let's say you want to simulate this transistor, and this is an NMOS type transistor. So for simulation, what I do, I just wanted to see this as a switch. Okay. So I just take a virtual signal from the palette, a square one, and connect to the one side of the drain, and make this guy as something like zero 0.2 low and zero 0.2 high nanosecond. This is the signal generator. So with the help of which you can generate various kind of signals like clock, pulses, or some analog signals. Okay, so I just assign it. And this is the source I want to observe, that what is coming at the output. So for any node you want to observe, you have to apply as a visible node. So click on this I like symbol and just paste over here, click over here, and you can say that this is my voltage output or any name you can give. That's it. But I am missing the gate. I mean, I have to apply something at the gate. So I can apply, I can make it always on, or I can make it off, or I can act as a switch that is on off like that. So I just place an square pulse on the gate, and I just place something like 1, or for 1 nanosecond will be on, and for 1 nanosecond will be off. Okay, that's it. I can just press this simulation button. There is a play button on the top menu, and just click on that, this one, and it should show you something coming at the output. I believe everyone is able to see this pulses coming at the output side. I just make this guy of 10 nanosecond so that we can see a long one. I can remove some flags so that the lines do not disturb your view. Okay. Okay, so you can see that this is my clock, the white one, and the first one is the input at the drain, because this was of 0.2 nanosecond, and this one is of 1 nanosecond. Okay, and the green one is the output. So what do we see? That for the zero input, sorry, for the zero input of the drain, I get a 0. Okay, and for the value of 1, for the value of logic 1, I don't get 1, isn't it? I gave him 1.2 volt. Okay, but okay, I pressed reset multiple number of times, and because of the transmission of the screen, it is running multiple number of times. Okay. Hmm. So do you see that you don't get full voltage? You are getting something like this, 0.7 volt. So you are getting zero point 0.7 something volt or 0.8 volt. So why there is a deduction of GST? Can anyone tell me? Are you guys familiar with this week 1, week 0 concept of the transistors, MOSFETs, that NMOS, and both they have to pay GST to the government, and there is some deduction of some amount of voltages at the output side. Are you guys familiar? Yes, no will work. No, no. Okay, okay. Hmm. Okay, no problem. All right, there is a couple of yes also, so I'm getting confused now. Okay, uh, let's
Yes, sir.
talk on it.
No, there
Are
might
you?
be some students, parents might be doing business, so they know aware of GST part of it.
Okay, the tax sum is low. Okay, so someone has raised hand. You can type your question there. Anyone has a question, maybe you can put on the common platform, and I will address it to everyone in a common way.
No, sir.
Okay. So if you have an NMOS, so generally they are used always on the pull down network. Why? Because the voltage across the drain to source, as the electrons are the majority carriers. Okay, so I mean, in a common format, I will say that the voltage across this is minus the threshold voltage. Okay, so whatever voltage you will apply at the drain, that will be subtracted by the threshold. Okay, so that means, and this value comes from you can say the mobility of the, or the structure of the transistor. So that means if you apply 1.2 volt here, and let's say the threshold voltage is 0.4 volt, so that means you will never get 1.2, you will get 0.8 volt at the output. Okay, so this is about the NMOS, whereas Okay, for PMOS, the story is reverse. The story is reverse. Okay, here you have this guy. So in basic format, you can say that it is plus. So that means if you give I mean, if you give a zero here, I mean, so what you will get? 0 plus zero point 0.4. So you will get 0.4 at the output. But if you give 1.2 at drain, so you'll get 1.2 plus zero point 0.4, 1.6. It is not amplifying, but actually you will get 1.2 only back. Okay. So that means PMOS is a producer of PMOS for 0 will give zero point 0.4. So this guy gives a weak 0 but strong 1. Okay, this is for PMOS. Whereas for NMOS, if you give sorry, not if you give 1, that is logic high, that is 1.2 volt, so it will give you zero point 0.8 volt. So that means he produces a weak 1 but a strong 0, because if you give 0 input, 0 minus zero point 0.4, you will get minus point, I mean, like you'll get minus zero point 0.4, although you never get minus values, but you will get 0. Okay, so you understand weak and strong ones and 0 concept. Oh, okay, I am by mistake, I stopped it. uh, are you guys familiar with the weak 0 and strong concept? Yes, it's reverse, I mean vice versa. Are you familiar with strong 0, weak 0 concept? Yes, I get a couple of yes. Yeah, that's good, great. So I just quickly cover it in case there are a couple of no's. So if you have an output of any transistor or logic families, let's say this is the V, ideally it should be V high and this is V low. Okay, so ideally the V low should be 0. Okay, and V high, let's say it's you are working on 5 volt technology, it should be 5 volt exactly. But if any of your output is producing which is not 0 but zero point 0.4 volt, zero point 0.4 volt, so you will accept as 0, but finally the output was not to the ideal level. That's why it is considered 0, but it is called as weak. It's just like getting a passing marks 37, you are passed but you are weak in concepts. Okay, and score anything above. So uh, NMOS is a producer of um, weak 1 but strong 0. Okay, that's why both complement each other. That's why they are Cmos together, they are a team. PMOS are always used for pull up, that is if anywhere you want to pull up any output you use PMOS, and anywhere you want to pull down anyone, okay, then you use an NMOS. Okay, so this is how the story comes. Because if we just clear this off, I just clear this design and make an PMOS. So I take a P diffusion and just click over here, draw a rectangle, and I know the size is 16 by 6 lambda, no problem. I take a polysilicon and draw a block in between. Okay, I'm not serious about dimension as of now, I would be coming to the dimension later. And I take an anvil because this PMOS has to be surrounded by anvil, because okay, let me remove the anvil and show you the 2D, not this one. So here you see this is the drain and source and the gate material. That looks great, but look at the bottom side. The gray area is the P-type substrate. So P-type diffusion on top of it, P-type substrate. No, this will not work. They will not make a reverse body. So an anvil has to be formed to make the reverse body of this transistor. Now, if you see the 2D cross section, then this is okay. That the P-type substrate, on top of it there is an anvil and drain and source. And even though in you see in 3D, this is how it is. There is an anvil, and in between the anvil there is an p-type material or the p-type diffusion. Okay, so let's simulate this. I do the same exercise. I take a square clock and give it to the input, and I take a visible node, put it at the source, and I call this as VO. Then I take a VDD supply and bias the NVL because this is important. Otherwise, the system will not respond properly. And I take another clock and put at the polysilicon gates and make it slower, make it one, and make it one. That's it. And if you want, you can change the color of the background screen also. You can just go to file, color, and white background. So this also is possible in Microwind. So here you can see that uh, if I'm giving I'm giving one at the output input, sorry, so I get zero point 0.4 something at the output. But if I give zero, okay, if I give zero, I don't get zero, I get zero point 0.4. But if I give 1.2 volt input, okay, then I get the same, okay, that I get 1.2 volt at the output. And remember, this is working as a switch, huh? It's working as a switch. He is only giving output when it is zero, when the input gate is zero. When the input gate is zero, then only he's producing the output. Otherwise, he's always off. Let me expand the gate. I double click on the clock and make it slower. So it becomes twice slower. So you can see the width of the input gate turn on off increased. So thereby you can see that the output has more number of pulses. So he's not producing zero. He's not going to zero. He goes to max zero point 0.4 maybe, yeah, 0.44 something. So that might be the threshold value of this transistor. Okay, and he's producer of weak zero but strong one. Hence, PMOS are used for pull-up network. Okay, so that is the first stage that you are trying to simulate transistors as a switch. Okay, and there is an option. I believe everyone is able to see the palette. So the palette will help you to access the different layers of the design. Okay, so there is an option over here in the palette. This is called as MOS generator. So with the help of which you can ask the software to generate a transistor for you. So I just click on this. So he will pop up, and by default he opens in the MOS option, and he asked me that, okay, what do you want to generate? An NMOS or a PMOS? What do you want to see? So I say, okay, make an NMOS for me. So I can specify the dimensions over here in micrometer or in lambda, both, anyone I like. So I just generate in lambda. So I can specify that, okay, the length of the MOS is 2 lambda and width is 10 lambda. And you can always play around and see the effect of it. You remember that the drain current is proportional to the W by L ratio of the transistor. That means it will increase with the width and it will decrease with the length. Okay, so I can just validate that. I just make the width as 12. So you see the current has increased. I make it 14, the current increases. I make it back to 10 and the current decreases. If I increase the length, I make it 3 lambda, you can see the current decreases. I make it 4 lambda, again it decreases. So more the length you increase, less. Sorry guys about sorry guys about the internet. It's Pune. Sometimes it just drops for a few moments. Okay, so we were at making something interesting. So I believe everyone has seen this mod generator. I just clicked on mod generator and made an NMOS of 2 by 10 lambda. And here you can see that he has made a beautiful, small, compact NMOS for you. And you can always see that in 3D and appreciate the construction that, okay, this is a metal layer on top of it. And these vertical ones are the contacts or the vias. And the red one, what you see is the polysilicon. And the green one is the diffusion. Okay. So let's make an inverter and you just take this NMOS little bit, some area. This time I select a PMOS. So I gave the same size, 2 by 10 lambda. And the current you can see is 0.27 something. And as far as I remember, the NMOS was having 0.378. That is 370 microamperes and 270 microamperes. So there is a difference in current. So the first question comes up, why there is a difference? And should we bother about of the difference or not? So anyone would like to discuss on this, that why there is a difference of current, why PMOS is less as compared to NMOS? Anyone would like to ask this question, or I assume that everyone is familiar with the concept? I just hold on for 5 seconds. Familiar. Okay. So NMOS has majority carriers electrons. Electrons has higher mobility, and hence they can carry the current much more faster and more, and hence they produce more current as compared to the PMOS in the same given dimension. Okay, it's just like petrol and diesel. Okay, the petrol has more combustion ratio and they are more powerful. That's why you can have a car made of 1000 cc of petrol engine, or even 600 cc in case of nano. It will work properly because it is able to produce enough amount of torque, whereas you can't do that in diesel. Has anyone seen a diesel engine that small? I mean, in the cars, 500 cc, 600 cc, or maybe 1000 cc, something like that. In bullet there was, I heard that there was a 500 cc diesel engine, but nothing in cars, right? So why? Because the diesel cannot produce that amount of torque in that given size, and hence it won't be feasible to drive the vehicle with that diesel engine. Anyhow, so we come back to NMOS and PMOS. So we just make a connection to these two one. So I can take metal one layer of the palette and draw the missing dots between these two lines, and maybe a little bit of extension. Then I take the polysilicon layer and draw this block in between, joining these two red blocks to each other. Okay, now this my inverter is ready, and I can simulate this and see the effect on the output. So I take a square clock, apply at the gate terminal, and I can describe this as 1 nanosecond low and 1 nanosecond high, and a visible node, because this is the output I want to see. I can call it as like V inverter. Okay, and I have to take a VDD supply connecting to the NMOS, this sorry, PMOS upper terminal, and a VDD supply for the NVEL, and a ground, okay, for the NMOS source. Okay, so here we have inverter which is ready for to simulate. So I just change the background color and run the simulation. Okay, yeah. So here you can see the delays, etc. So this is working as an inverter. You give 0 at the input, you get 1.2 at the output, you give 1.2, and you get a 0 at the output. So it's working perfectly. You can see the power consumption, which is around 0.68 microwatt. So this is the dynamic power consumption consumed during this simulation run. I mean, from 0 to 10 nanosecond, how much power was consumed. This is what he's showing. Okay, so to make something interesting, I take a virtual capacitor from the palette. I take a virtual capacitor and attach to the output, and let the value be very small, 0.005, a very small value, and I can change the color and simulate this. So here, what do you see? That yes, it's still working as inverter. There's no harm in it, and the rise time is around close to 18.9, and the fall time is 14.4. Is this okay? And maybe in the next simulation, I just double click on the capacitor and increase the capacitance value, double it. Okay, so this time you see the rise time has climbed to 31 almost, or 30 point something, and the fall time is 23. So there is a difference in the rise and fall time. So why there is a difference in rise and fall time? Are you guys familiar, or you wish to discuss this? So I can just have quick yes or no, y or n, that if you guys are familiar that why there is a difference in the rise and fall time. You can just type yes or y. Okay, if no, then you can just type no on n for short. So I get a couple of yes. So
Yes, sir.
okay, so there is a difference because there is a difference of current also. Okay? Current you can always relate to the torque of the car. Remember this. Okay, the torque of the car is because of the cc of the engine, and same is with here. The torque of the current, or the current of the transistor, is dependent on the size of the transistor, and the torque produced by the transistor, or the current produced by the transistor, is equivalent to the speed. Yes or no? Right, I believe everyone would try to make a relation to it. So remember, you have a 100 cc engine. The 100 cc engine is producing some torque. Okay, with that torque you can achieve some speed. Okay, so this is how they are connected in series. It's not like this the speed is more because engine is bigger. Okay, but then you have to go stage by stage. Okay, the same is with transistor. The current of the transistor is dependent on the size of the transistor. Okay, the size of the transistor, you get current from the transistor, and from the current you get the rise and fall times. Okay, so higher the current, faster is your rise and time. Okay, and slower the less the current, slower would be your rise and fall time. Okay, if tell me now, uh, if I just make this capacitance as maybe 3 picofarad. Okay, what is happening now? If I ask you that uh, I have just changed the capacitance to 3 picofarad, a very big value, I know, kind of cheating, but okay, I like to do that on monsoon days. So what is happening to the output? Is the inverter gone faulty? Is the software gone faulty? Something wrong in the capacitor? Did I type 3 picofarad or 3 microfarad? Or um, something else reason is there? Or all of a sudden I have activated a triangular wave generator of the inverter. So filtering. So this is, he's doing filtering. Okay, no problem. Okay, there's, I have one answer that the inverter is doing charge discharge time is more than the clock. Okay, there's one more answer. Any couple of more answers, then we will talk more on it. The capacitor is still charging. Okay, maybe I give him more time. I just, instead of 10 nanosecond, I make it 100 nanosecond. I remove the delay because otherwise it is producing the vertical lines and difficult to see. So I run the simulation for 100 nanosecond and still I see no sign of charging. Maybe I can go till the more extent. I simulate till 500 nanosecond and still there is no sign of rising. And he's just going up and down and up and down. Any, a couple of more answers will help me in progressing, because I still had only two, three. So I just wanted to make sure that you guys are listening and not sleeping or watching other movie stuff side by side. Just kidding around. Okay. Can I have a couple of more answers?
Filtering only, sir.
Okay, so you can speak also if you want. I believe everyone has given mic independence. You can speak, I believe. Or shall I unmute everyone? Yes, you're allowed to unmute yourself. And if someone wants to talk and speak, then what is going wrong?
They can unmute and they can speak.
Yes, they can speak if they want wish to. Otherwise, maybe another 5 seconds and I start. Okay.
Because of the capacitor charging.
Hmm. Okay. Yes, that's what we increase the capacitor, and but the problem is he's not able to charge. He's not able to charge. Charging time is high. Yes, that's right. Okay, let's take some couple of examples, real life examples, so that you can always remember that how they are linearly connected to each other. You had a 100 cc bike, okay, and when you sit on the bike, you just sit on the bike and you give the throttle and you reach from 0 to 100, let's say in 1 minute, okay. So now you make, one more guy sit on your bike. Now you start again from zero. So do you think you will be able to reach 100 kilometers per hour at in 1 minute? Probably no, right? You will take more than 1 minute, because as the load increases, you require more time to lift the load to that level. Okay. Now, if you now what we have done just now, that on one bike we have placed 10 people on it, or maybe 300 people on it, isn't it? Because from point zero 0.01 we jump to 3 picofarad. So what is happening now? There are 10 people sitting on the bike, and the bike will not be able to reach 100 kilometers per hour. It will just move ahead a little bit, and he's able to hold that position like that way. So this is the same the capacitor is doing. Okay. So either you give him ample amount of time to charge to that value, because what is happening when the capital starts rising, okay? I just take it, maybe just a print screen. I just take the print screen. Yeah. So when this is zero, so you were rising the output, you were increasing the output. You are expected to go like this, okay? But you are not, because as the capacitor is very high, so the output charging time is also huge. So you take some time to charge. But before you could charge the output, you gave him discharge command, because it is the input was zero, and now you have made the input as one here, okay? I believe. Sorry, I didn't. Oh, okay. Are you able to see the screen? Because I'm not sure that if this guy follows what I'm doing. Okay. So I was trying to draw this stuff for you guys. Okay. So what is happening is that you give him zero, and something like 1 like this. So when you give him 0, so output try to charge the output, okay, the inverter. But before it could charge, because the charging time has increased now drastically by 300 times. Before that, you are giving him a discharge command. So he starts discharging. I mean, he goes down, okay, and he will keep on doing that forever. So he will be never be able to charge, okay. It's just like you had a small bucket first, right? You had a small bucket first, and so it was filling at less than 1 minute. But now you have made a big bucket. So do you really expect that this will be filled in 1 minute? No, it will take more time to charge. Okay. So what do you do? So you give him time. So I just double click on the clock. Uh, are you able to see Microwind screen again? I believe he's giving me something pause message. Okay. I just share it back again. Okay. I just checked what is wrong with my sharing because he's showing that I have stopped sharing, and just a minute. Yeah, I believe Microwind is showing now. So either you have to give ample amount of time to charge. Okay. So to do that, I just double click on the gate clock and make this guy as 20 low and 20 high instead of 1, and simulate again. Now let's see what happens. And I increase my time scale to 100. Now you can see the output is able to charge and discharge. Okay. So I can ask him to show me the delays so that I can see that how much time it takes to charge and discharge. So it takes almost 7 nanoseconds and 4 nanoseconds, 5 nanoseconds to charge and discharge. So that's in huge values. Okay. So either I have to slow down the input clock to charge and discharge that amount of load. So it will take huge amount of time to charge the output. Okay. But let's say my design requirement is such that I have to design an inverter which can drive a load of 3 picofarad, okay, which can drive a load of 3 picofarad at the rate of maybe 500 megahertz. Because if you look at the frequency, I just increase the step size so that it becomes faster. If you look at the frequency, it is 25 megahertz, okay. This I'm operating at 25 megahertz if I take the input clock. Yeah, this is 25 megahertz input. Okay, so this is very slow one. I want something, make an inverter who can invert a signal of 500 megahertz, and that too with a load of 3 picofarad. So what shall I do? Can I have some answers on this? uh, are you clear with the question? That I have to design an inverter, okay, inverting an 500 megahertz clock with load of 3 picofarad. So what would be required? What would be required? Can I have some voice answers, because I think that would be faster? Because if you guys type, that will take a long amount of time. So I can appreciate voice answer. Am I audible?
Yes, yes.
Yes, sir.
Yes, I'm audible. Okay, great. So anyone wishing to come forward and put his view and opinion on this? You saw this inverter. We placed a load of 3 picofarad, but he was not able to charge and discharge the capacitor. If you have to charge and discharge the capacitor, you have to slow down the input. You have to give ample amount of time to charge and ample amount of time to discharge. Okay. But in my design, I require an inverter who can invert a 500 megahertz signal with a load of 3 picofarad. I'm not adding some other parameters like rise and fall time that guys, I want a rise and fall time less than 100 picosecond also. That can be also added, but I will not make that complicated in the first shot. Okay, so what shall be done? What can be done? What steps you will follow? This guy becomes complicated. Reduce the voltage. Okay, it's just like you want to beat Ben Johnson in an 100-meter race. So uh, it's like that he takes 10 seconds to reach the 100 meters. So if you want to win, make the distance as 50 meters. Okay. Anyone else? You can put audio answers. That will be quick and faster. It's up to you. I mean, if you guys want to type, then the typing also can be an option. I hope I'm audible because I didn't got confirmations.
Yes, sir.
Okay, great. So anyone would like to put an opinion on this? Okay. Decrease distance between source and
Not understood, sir.
no problem. Okay. So the question is that uh, you have to invert a 500 megahertz signal, okay, with a load of 3 picofarad, okay, and your rise and fall time should also be less than rise and fall time should be less than 50 picosecond. This is, oh sorry, I placed a personal message. It should be everyone. Yeah. Okay. So you guys have to design an inverter which can invert a 500 megahertz clock with a load of 3 picofarad. What you will do? Is the question somewhat clear? Is the question clear, or I was very complex in making this question?
Question is not clear, sir.
Okay. Okay. So you guys saw this inverter. Any doubt in understanding an inverter function? I believe everyone have understood this inverter design. A simple inverter we have made, and earlier I simulated this at the speed of what? 5 nanosecond I give it. You remember this? This is what we were getting. You remember this? That I was trying to invert an signal of 100 megahertz. Let's say this is 100 megahertz signal. You see on the top side, this shows like 100 megahertz over here. This 99.5 megahertz. Okay. So I'm trying to invert an 100 megahertz signal, but I can't. You see a triangular output. Okay. Now, why is that? Because the load is very high. The load connected to the inverter is of 3 picofarad. That's a huge value. Okay. So, but still I'm adamant. I'm like, my design has that requirement that I have to invert a signal of 500 megahertz, not even 100. Or let's say, okay, we continue 100. There's no harm in that. I'm not, you know, adamant on doing this. So even 100 megahertz signal, if you take, okay, and you have to invert this, but the load has to be of 3 picofarad. It has to be 3 picofarad load, and the rise and fall time should be less than 50 picoseconds. So what you will do? What's what idea you will put forward to do this? Okay, maybe add another capacitance. Okay, maybe I reframe the question again. Try to listen this now. I have a bike which is of 100 cc. Okay, and I try to throttle it, and I reach 100 kilometers per hour of speed. Okay, in 1 minute. Is this okay? So that 1 minute is my rise time. 100 kilometers per hour speed is my the high and low, what you can say. Okay, okay. And but now what is happening, instead of one person, they are 10 people sitting on the bike. So my question one, can your bike reach, can your 100 cc bike can reach 100 kilometers per hour of speed? That's question number one. That's the question number one. क्या आपकी बाइक 10 लोगों को बिठा के 100 किलोमीटर पर आवर की स्पीड पे पहुंच पाएगी? Okay, probably no. Okay, my second question is कि आपको ऐसा करना है, आपको 10 लोगों को बिठा के बाइक को 100 किलोमीटर पर आवर की स्पीड पे चलाना है. ओके, और आपको वो 100 किलोमीटर पर आवर की स्पीड जो है वो 1 मिनट में पहुंचनी है. इट शुड बी अ 1 मिनट. In less than 1 minute, 10 people sitting on a bike can reach a speed of 100 kilometers per hour. So what you will do? Now maybe forget the Cmos technology uh, for a minute, and yes, you will add a resistor in the bike. Where? You will add a resistor in the bike. Okay. Jet fuel should be used. Okay, I give you a Splendor. I give you a Splendor and put in jet fuel in that Splendor. Do you think that you can fly in the air? Uh, Increase power, change bike, improve performance of the engine. No matter how much improvement you make in a 100 cc engine, there will be an always an upper limit. Increase efficiency, and 100 cc bike is working at an efficiency of 90%. Even you will not be able to reach that mark. So you have to see. Remember, we tried to relate in the forward direction. Now, yeah, this time you have to come backward. I said that for an engine and a transistor, the cc is the size of the transistor. Okay, when you say that my bike is 100 cc, okay, that is the size of your engine. Okay, and when you say your transistor is w by L ratio, your w by L ratio, let's say in our case it was 10 and 2, so that is 5. Okay, w by L ratio was 5. Okay, so you have a ratio of 5. So that 5 is nothing but the cc of your inverter or the transistors. Okay, so your size of the transistor and size of the engine will give you some torque. Okay, that will give you some power, or it will give you some torque. That torque is nothing but the current in transistors. So size of the transistors will deliver a current. Okay, more the size, more the current. Less the size, less the current. Simple as that. Same is with the engine. More the cc, more the torque. More the cc, more the torque. Less cc, less the torque. Simple as that. Okay, now what happens with the torque? What happens with the current? More the torque, faster is the speed, isn't it? Why a bullet bike goes faster? Because it has more torque. And why is there is more torque? Because it has a 350 cc engine. Simple. Okay. Why doesn't Harley Davidson bike move the fastest? Because they have higher torque. And how they have a higher torque? Because they have a higher size engine. Simple as that. Same is with the transistors. If you want more current, increase the size. More current, increase the size. Less current, less size, smaller size, right? Okay. So now if you have to sit, so this is the reverse calculation you have to do, that there are 10 people sitting on a bike. So like, and I have to reach 100 kilometers per hour of speed. So you need to reverse calculate that I will require at least 100 Newton meter of the torque. Let's say this is what the kind of reverse calculation you do, that for 10 people reaching an 100 kilometers per hour speed, I will require 100 Newton meter of the torque. So you just search the bike catalogs and you find that yes, Harley Davidson, this particular model will support this my requirement. and that may be having a 1000 cc engine. That's it. So you just look at the torque chart and you look at how much amount of cc that bike has. So you find that this was 100 cc bike will produce that amount of torque, and you buy that one. Okay, or maybe you just fabricate your own engine for you. The same is with the transistors. That okay, you have a load of 3 picofarad, you have to reach at the highest level. That is, you have to switch from low to high. Okay, at a given time frame. So you will require at least maybe 5 milliampere of current. So to get the 5 milliampere of current, what is the ratio of the W by L I require? So that you can tell the software. Okay. So let's do this quickly and then we can close for the day. Okay. So this time you can just have a look, but don't follow through because I don't think so. It is that complex that you will not remember those steps. And I'm sure everyone would be able to follow this. So I again go to MOS generator. So I did some reverse calculation. I found that the NMOS W by L ratio should be 100 or maybe 50 or maybe 150, maybe 140, no, 150. Okay, so around 125 lambda is the width of the NMOS and 2 lambda is the length. At that time, the transistor will produce a 5 milliampere of current. So 5 milliampere, I did the reverse calculation that 5 milliampere, I did the reverse calculation that for 3 picofarad of current and 50 picosecond of rise time, what is the RC time constant, and accordingly how much R is there, and accordingly V by IR, I did the reverse calculation that how much of current is required. So 5 milliampere is the current required. So I just place an on the clipboard. So this is what you can see, that this is the big size of transistor I generate. Now I require 5 milliampere of the NMOS also because it requires both. But due to the issues of the mobility, I have to give him higher size. I make it 150, no, around 160, 175. Yeah, for 175 width and 2 lambda, I will get 5 milliampere of current from PMOS also. I just place on the clipboard. That's it. And I zoom this area. Okay, just for you. Okay. Now I just take the polysilicon and join these two blocks. Okay. So the gates are shorted. Then I just take the metal layer and short these 2 points. Okay. So drain and source of the NMOS and PMOS shorted. I take a square clock, apply it to the gate. And this time again, 1 nanosecond high and 1 nanosecond low. And this is the visible node I want to see. So I just call this as V output. And I take a virtual capacitor and attach to the output node and make it of 3 picofarad. And I take a VD supply and PMOS right inside this terminal, and a VD supply for the NVL also. Both have to be biased. And then I take a ground signal for the NMOS other side terminal. That's it. So we are ready to go, I believe. I just change the background color and some lights. Okay. So this is 500 megahertz speed. I have to reduce to 100 megahertz because uh, finally we talked about this 5 and 5. So here you can see that this is 100 megahertz speed, and this guy is able to charge and discharge properly. The rise time and fall time are almost of the same order. It's around 400 picosecond. Yes, not 50 for sure. So that means my current is less. Still my current is less. 5 milliampere was not the right calculation probably. It should have been maybe 8 milliampere at least, or even more, maybe 10 milliamperes. Okay. So, but then we have solved one problem, that yes, we have understood one thing, that if the load is higher and we want less rise and fall time current, so obviously we have to increase current. And to increase the current, you have to increase the size of the engine. You remember this? Okay. So try to always correlate that way. Okay. That size of the engine, torque of the engine, performance of the vehicle. Okay. This is how they are connected. If you want higher performing vehicle, okay, then you need to increase the size of the if you want to, you have to increase the torque, and to increase the torque you have to increase the size of the engine. Okay, this is all correlated. Okay, is it okay if anyone has a doubt on this? uh, you can ask a voice question, that will be better. Okay, and at the same time, at the same time, also remembers capacitance will draw power. Look on the right hand side window of the microwind, just above the close button. The power is how much? It's half milliwatt almost, zero point 0.4 milliwatt. The power has gone up, isn't it? Yes or no? Yes, it has gone terribly higher. Okay, because power is proportional to frequency into capacitance into voltage. So frequency, yes, we are increasing. Secondly, the capacitance was huge. We are driving a huge capacitance. The current drawn are also huge. If I ask you which is more economical bike, Splendor, which is of 100 cc, or Harley Davidson, which is of 1000 cc fat boy types. Okay, so I believe everyone will agree on this that Harley Davidson gives a much lesser average as compared to Splendor 100 cc. Okay, so 100 cc bike, smaller engine, less current, less performance, and much higher economy. Whereas the reverse side is Harley. You get best performance, best torque, everything is good except the economy. Okay, you have to refuel the bike after uh, every decade of kilometers. Okay, so this is all about microwind. So this is only the inverter we have covered. I've just touched the subject and I've just touched the software. There are many more, variations and tuning of the concepts you can always play around, tweak around. So this is the power of microwind, that within few minutes you can touch the subject and play around the circuits or in variety and understand the concept in a much more deeper manner. Tomorrow we
Yeah,
will
Vinayji,
yes
just
sir.
I want to know, like, see, many some colleges has got cadence tool also in their college, and mental graphics tool also.
Yes
Like,
sir.
what is the easiness of using this microwind tool compared to those two?
Uh, it's a big difference, sir, because thus inverter what we have made in 5 minutes, it will maybe take 4 5 days doing in those software. Because in those software what happens, they are project settings are required. You have to configure the libraries, you have to configure the design rules, you have to uh, set the design flow of the tool itself, and then you have to draw the schematic, convert into an netlist, and then pull up in the layout format and ask him to make the layout by hand or even using the design toolkits. So it's a hell of design process. So they are not focusing on the education part, the learning process. They are focusing more on towards the serious design process. So that's a big difference. So Microwind allows to learn quickly. The learning curve is very short, and it allows you to play with variation of the circuits possible in the shortest time given.
Yeah, is there any
And
possibility where we can use a schematic and then come to the layout also
yes, we can do that. I will
tomorrow?
explain that in the later part of the courses, definitely.
Okay, sure.
Yes.
Okay.
So maybe tomorrow you can all come by playing with the software. I've already given you the license file. So you can just draw the same inverter, try running a load of 3 picofarad or maybe 2 picofarad, and try to achieve oscillations within speed of 100 megahertz and see how you can achieve that. Okay. So that can be assignment for you guys tomorrow. So tomorrow again we will start with inverter, and we will do at least 3 4 flavors of inverters. Okay, because we will proceed further with other experiments, because I love inverter so much that I can spend at least a week on talking on inverter. But I will wind up tomorrow. Don't worry. Okay.
Uh, So, okay, one more thing.
Yes,
Just
sir.
I want to know actually like feedback from the students. Today I have not taken the poll, but if everything is okay, please say yes or no, so that if anything, no, they want any some additional things to be changed, okay, let them write on the chat box.
Yeah, sure.
Students, go ahead again. Or you can come on audio also, no issues. If you are cleared, then okay. If not, no, you can ask question also. Virenji, your YouTube channel, I think you can share it in the chat box.
Okay, I just get the link.
Sainag, not understood completely. I think you didn't attend in yesterday's class. Sainag. Last part of little confusing. Okay, what is confusing? Can you the concept transformation? Microwind tool has structurally in 3D, which helps us visualization. Correct.
Okay.
Yeah.
Uh,
Okay. Today is the
yes,
first
this
class. Yes,
is,
sir.
yes, okay. No problem, Sainak, because yesterday there were few stuff covered to talk about it. No problem. We will try to cover your doubts in the later part of the courses. And I've just based my channel's videos. I've started uploading during this lockdown activity. I'm not in that serious YouTuber or stuff. So I placed some videos on channel, but I will be posting more videos. I prepared some videos, but they are yet to be posted. So as the time will permit, I will keep on doing that. So in the meantime, you can use whatever contents you can make. There is a FinFET inverter is there. The steps are almost the same. There is steps are same, so you can use the same one. Okay. I think inverter. I'll just click on this. Yeah, this is the link for a demo of the inverter.
Yeah, students can copy that.
No problem, Swati. We will discuss more on this concept tomorrow. You just, it's a big tablet, so don't try to digest everything in one day. Don't expect. No problem. Slowly, we will take the concept further. Okay, because you have to understand the size, current, and the size, torque, and performance connectivity. Okay, so slowly we will take further. Don't worry. So I believe at this
Any other
stage,
feedbacks?
rather say you can make and some common file link where everyone can write their doubts,
What
and
we'll
I
do
can.
actually,
Yes, sir.
students, actually, what we'll do, we can have a one Word document. It is open in Drive. If any of the questions, students can put it in that file. So that any all these questions will be answered by Mr. Vinay, and then later actually everybody can see that answers. So that could be better option. See, if it is a WhatsApp or anything, you will miss many things. Okay, see, these documents should be recorded, and you can use it later part also. Is it okay?
Yeah, cool.
Yeah. Okay, I'll send. I'll create that Word document file, and then I'll forward to everybody. Thank you.
Okay, sir.
Thank
Sir,
you.
we'll see you tomorrow.
Good day.
Bye bye.
Bye.
Bye bye.